we will begin our study of the derivative with the definition, but first maybe a picture to illustrate. So imagine, use black, imagine we had a graph, and this will make it simple as y equals x squared. Right, so we know it's a parabola. And what we're able to do easily is take one point on this graph and another point on this graph, and we can find the slope of the tangent line. Right, and this is a pretty good approximation for the slope here. Right, the slope at a point. But if we imagine the same picture, so just grant me that this is the same picture, it would be even better if we used a point closer to where we're actually looking, right? That the slope of this secant line is a better approximation for the slope here. And if we could get closer, and again, just grant me that this, please grant me that this is roughly the same picture. That would be even a better approximation if we could use this secant line. And what we're doing to say what the slope is at this particular point, and what we're doing is we're getting the distance, the x distance, the horizontal distance between the 2 points is shrinking. And if we could get that distance to be 0, that is, as the distance between the 2 points horizontally gets smaller and smaller and smaller, we're getting more and more accurate with what the slope is at a particular point. And if it was 0, that would be the best thing possible for us. Right? So the idea is something along the lines of that the slope at a point would be best approximated if our points in question, right, if the points we're using are infinitely close or infinitesimally it's probably not spelled right. Right, really small, infinitesimally close. And we define this thing, this idea, to be the derivative. Right? In one sense, the derivative is an expression, the derivative of a function is an expression for the slope, or the rate of change, more importantly. At a given x point, or at any x value. So we're talking about the rate of change of the function when we're talking about the derivative. Now, for purposes of the AP exam, this definition is important. Right? So if y equals f of x, the derivative of f is, the notation for this, and you really need to have this memorized, f prime of x, which is the notation for the derivative of a function, is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Now notice that this is just the slope formula. Right? We've got our y value at f of x, a different y value, f of x plus h, that's close to f of x, and h is the change in x, right? It's the difference between the two x values. And as the difference between the 2 points goes to 0, we've got the derivative, right? So this is really the slope formula as the denominator goes to 0, right? And this is the derivative when the limit exists, right? If the limit doesn't exist, then we don't have a derivative there. Right, but this is the idea, and this is the limit definition of the derivative. So, next example, first example, with regards to it. And we're going to focus on the limit definition for a moment. So let's imagine that what we have is f of x, that's our function, equals x squared plus 2. And what we'd like to do is find the derivative of this. Well, by definition, the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Which means that what we're looking for is the limit as h goes to 0. F of x plus h is x plus h squared plus 2 minus f of x, which is x squared plus 2, all divided by h. Now currently, we can't solve this limit by substitution because we end up dividing by 0. So we're going to need to do some algebra to use the limit definition. If we expand in the numerator, we've got x squared plus 2xh plus h squared plus 2 minus x squared minus 2 all over h. And I should have in here somewhere, because we haven't taken the limit yet, the limit as h goes to 0. Now this is nice because this will simplify. So we've got the limit as h goes to 0. In the denominator, the x squared subtract out and the 2's subtract out. So we're left with 2xh plus h squared over h. And now the h actually divides out, which is what needs to happen so we can take the limit. We're left with the limit as h goes to 0 of 2x plus h. When h is 0, we're left with 2x, which means that if f of x is the function x squared plus 2, then its derivative is 2x by the limit definition of the derivative, right? We've shown what the derivative is equal to. So that's our first application.